Prepare to have your cosmic perception shattered as we embark on an interstellar voyage to TOI 3757b, a nightmarish exoplanet in the vast expanse of the known universe. Peculiar? Undoubtedly. However, our planet is profoundly enigmatic as well. It is not illogical to assume that the cosmos, an expanse overflowing with numerous galaxies, each possessing billions of stars and an unfathomable multitude of planets, would have such ethereal quality. Within the awe-inspiring depths of the cosmos, nestled about 580 light-years away from Earth, in the magnificent Auriga the Charioteer constellation, NASA discovered a mysterious, horrific exoplanet. The TOI 3757b is a mysterious gas giant planet that elegantly orbits around its star, a brilliant K-type star. TOI 3757b has a mass of 0.26838 Jupiter, which is quite impressive in and of itself. However, what truly makes this planet stand out is the fact that it takes a mere 3.4 days to complete one orbit of its star. That's right, you heard correctly. 3.4 days. Such a short orbit time is a testament to the bewildering nature of this planet. This celestial body was discovered in 2022, permeating the realms of human consciousness. As astronomers and astrophysicists shared their incredible discoveries, the world held its breath in eager expectation, preparing to be opened to information that would eternally transform our understanding of the universe. As if its distance from us wasn't enough to make our heads spin, this planet boasts of being the lowest density planet ever detected around a red dwarf star. This means that TOI 3757b has an average density similar to a marshmallow. If you place it in a tub of water, it will float. Can you even imagine that? As stated by Shubham Kharodia, who is the first author of the paper and a diligent researcher at the well-reputed organization behind this study, the mass of the TOI 3757b was gotten using the vast and valuable data obtained from NASA's TESS mission and the Red Buttes Observatory. TOI 3757b has a mass approximately 0.27 times that of Jupiter, with a radius about 1.07 times that of Jupiter. As a result, its average density is about 0.27 grams per cubic centimeter. This implies a density lower than that of water, and even lower than that of air at sea level. In comparison, Jupiter boasts of a density of roughly 1.33 grams per cubic centimeter, while Earth has a density of about 5.51 grams per cubic centimeter. The remarkably low density of TOI 3757b increases the mystery surrounding it, considering its orbit around a red dwarf star, a star known for being the smallest and dimmest yet capable of sustaining nuclear fusion within its core. Red dwarf stars, the smallest and faintest members of the main sequence stars that sustain a steady conversion of hydrogen into helium nuclear fusion within their cores, can be surprisingly active despite their relatively low temperature compared to stars like our Sun. Red dwarf stars exhibit high levels of activity and are prone to violent flares that can strip away the atmospheres of neighboring planets, rendering them inhospitable to life. That makes it more surprising that such an ethereal planet could thrive around such a hostile star. The considerable separation between TOI 3757b and its stellar host exposes the planet to intense stellar radiation and gusts of wind that possess the potential to erode its atmospheric layer over time. Furthermore, given its proximity to the star, it is highly probable that TOI 3757b is tidally locked, meaning that it perpetually faces the same side towards its star. This aspect generates enormous temperature disparities between the planet's daytime and nighttime sides, thus posing additional challenges for any hypothetical life forms. TOI 3757b's exceedingly low density denotes that the planet possesses an extensive volume relative to its mass. Consequently, It is possible that the TOI 3757b either has a tiny central core or none. The core is very vital in generating a protective magnetic field around the celestial body, shielding it from the onslaught of stellar winds and cosmic radiation. The absence of a magnetic field renders TOI 3757b more susceptible to atmospheric erosion and radiation-induced harm. Furthermore, the planet's low density suggests the existence of either a thick envelope of hydrogen and helium gas or a notably dense atmosphere. A voluminous atmosphere could generate a greenhouse effect, rendering the planet excessively hot for life to survive on it. Alternatively, an extended gaseous envelope could render the planet more susceptible to atmospheric loss as a consequence of stellar heating or tidal influences. Scientists have put forth two potential explanations for the planet's low density. The first suggests that TOI 3757b formed during the late stages of its star system's history when there wasn't sufficient solid material remaining to facilitate the formulation of a substantial core capable of triggering runaway gas accretion. The second suggests that the planet experiences powerful tidal heating due to its eccentric orbit, causing its interior to expand and consequently reducing its overall density. TOI 3757b was initially detected through NASA's Transiting Exoplanet Survey Satellite, TESS, and subsequently verified using the Habitable Zone Planet Finder, HPF, on the Hobby Eberly telescope, as well as the NEID instrument on the WIYN 3.5-meter telescope. Launched in 2018, TESS is a NASA mission designed to identify numerous exoplanets orbiting nearby luminous stars. TESS achieves this feat using 4 cameras to observe different regions of the sky for 27-day intervals, collecting data every 2 minutes for approximately 20,000 stars within each sector. Among the stars under TESS's scrutiny was TOI 3757, a red dwarf star with a mass approximately 0.6 times that of the Sun and a radius roughly 0.6 times that of the Sun. TESS detected 4 distinct transits of TOI 3757b, occurring at intervals of 3.4 days, and each episode spanning for approximately 2 hours each. For context, a transit happens when a planet, from our vantage point, passes in front of its star, leading to a mild diminishing in the star's brightness. The transit depth of TOI 3757b was estimated at around 0.8%, denoting that the planet obstructed roughly 0.8% of the star's light during the transitory phase. This information, in turn, helped the scientific community to estimate the planet's dimensions relative to that of its star. However, to clear any doubt of the transit signal being a product of another phenomenon, like a background eclipsing binary or stellar activity, additional data from radial velocity measurements were necessary. Radial velocity is a method employed by astrophysicists to gauge the magnitude of a star's oscillation induced by the gravitational enticement of an encircling celestial body. Picture this. As the celestial body traces its orbit around its star, it causes a slight movement in its star's trajectory, tugging it slightly closer and then farther away from our vantage point. This cosmic tug-of-war causes a shift in the wavelengths of the star's luminous emissions, under the Doppler effect. Delicate, yet profound. Through the longitudinal assessment of this displacement across time, scientists can deduce the mass and orbital characteristics of the celestial body. HPF and NEID are 2 cutting-edge spectrographs expressly crafted to measure radial velocity measurements with utmost precision and constancy. HPF has been integrated into the monumental 10-meter Hobby Eberly telescope, located at McDonald Observatory in Texas, while NEID, a formidable force in its own right, finds its place within the 3.5-meter WIYN telescope, situated at Kitt Peak National Observatory in Arizona. Both instruments meticulously watched TOI 3757 for numerous months, unveiling a cyclic radial velocity pattern characterized by an amplitude of approximately 30 meters per second. This value corresponds to a planetary mass roughly equivalent to 0.27 times that of Jupiter. The radial velocity pattern is impeccably aligned with the transit signal generated from TESS. thereby confirming the verifiable existence of TOI 3757b as a real planet. TOI 3757b represents an excellent opportunity for scrutinizing theories regarding the formation and evolution of planets surrounding red dwarf stars. It also serves as a valuable subject for investigating the atmospheres of climates of gas giant planets in the most extreme of environments. One of the ways scientists can gain deeper insights into TOI 3757b is by conducting transmission spectroscopy studies utilizing either existing or future telescopes. This form of spectroscopy gauges how different wavelengths of light are absorbed or scattered by the planet's atmospheres as it passes in front of its star. This analytical approach can unveil vital information about the atmosphere's composition, temperature, pressure, and structural characteristics, and the potential presence of clouds, hazes, or rings. TOI 3757b stands out as an ideal candidate for transmission spectroscopy due to its massive size and low density, which amplify atmospheric signals. Furthermore, its orbital path encircles a luminous yet diminutive star, magnifying the contrast between the starlight and the planetary shadow. Additionally, the planet exhibits frequent transits, facilitating multiple observations that enhance the accuracy and precision of measurements. Using the HPF instrument, scientists have already conducted transmission spectroscopy on TOI 3757b, focusing on the helium-10-830A line, which is sensitive to atmospheric escape mechanisms. However, no evidence of helium absorption was found, indicating that the planet either lacks a substantial helium envelope or possesses a lower than anticipated rate of helium escape. Dr. Jessica Libby Roberts, a postdoctoral researcher at Pennsylvania State University, stated that employing cutting-edge technologies like the NASA, ESA, CSA, James Webb Space Telescope can be used for future observations of the TOI 3757b and will shed more light on the puffy nature of the planet. This suggests that upcoming observations with more advanced instruments can delve into the other wavelengths and molecular constituents such as water, methane, carbon dioxide, or oxygen. Such investigations could offer additional insights into the origin, evolution, and ultimate fate of TOI 3757b's atmosphere. Dr. Canadia expressed, finding more such systems with giant planets, which were once theorized to be exceedingly rare around red dwarfs, is part of our goal to comprehend the intricacies of planet formation. Hence, the quest to understand planetary formation can be further advanced by undertaking dynamic studies, analyzing numerical simulations, or analytical models. These studies scrutinize various aspects, including the planet's orbit, rotation, shape, and internal structure. And that brings us to the end of this video. What do you think about this fluffy exoplanet? Let us know in the comments section. Keep exploring, as always.